In this video, we're going to be explaining a PhD comprehensive exam Rossby Waves linearization problem for graduate level atmospheric dynamics. And for those of you taking atmospheric dynamics, so the dynamics of meteorology, sometimes called, you'll want to pay attention to this problem because you'll want to know how to understand what is a Rossby wave. That's today on High Peak Education. What's going on, everybody? Hope you're having a wonderful day. And I got a comment from a listener that wanted to say, hey, when are you going to post other parts of the video? So this is actually going to be sort of part 0 because we're going to be posting about what the problem setup is. So the problem setup will be this video, and then we'll have a subsequent video which will be part 2, which will finish sort of solving the problem at a later time. This is a follow-up to a video that I made several years ago, but it's actually gotten a bit of traction, and I think those of you who are studying atmospheric dynamics want to know what the solution to this problem is. So let's get into today's content explaining the atmospheric dynamics problem. So for this video, I just want to set up what's going on with this Rossby Waves problem. This is Rossby waves in a stratified atmosphere under quasi-geostrophic theory. So this is previously a exam question as part of a comprehensive exam for an atmospheric science graduate program. So let's take a look at what the problem says. It says the quasi-geostrophic potential vorticity equation for a three-dimensional atmosphere with stratification given by the Brunt-Weissele frequency n of z is this: dq dt equals 0, q equals nabla squared, sometimes called del, the del operator squared, psi plus d by dz, that's partial derivative with respect to z in the vertical, f naught squared over n squared, partial psi partial z plus beta y. Now a couple things as far as what do some of these symbols mean here. Z is the vertical coordinate and x and y are horizontal coordinates. Typically the x coordinate is going to be east and west, and the y coordinate is going to be north and south. We're assuming here a beta plane. East is in this direction, north is in this direction, and vertically upward is in this direction. So the positive x direction is going to be east, the positive y direction is going to be north, and the positive z direction is going to be upward. Okay? So imagine that each of these is perpendicular to one another. I try to do my best here to draw some sort of three-dimensional axis. Also note that f is what we call the Coriolis parameter. So f and the 0 means constant, nearly constant on this beta plane. F0 is going to be 2 omega sine phi. And phi is going to be the latitude. That's typically going to be in degrees. Capital Omega here is going to be the Earth rotation rate. So the angular velocity of the Earth rotation rate. And then that would be in units of radians per second. And in order to calculate this, what you should do is you should take 2 pi and divide by 24 hours. Now, by the way, when you work all that out, you get about 7.27 times 10 to the minus 5th radians per second. That's the Earth's angular rotation rate. Anyway, this Coriolis parameter, notice it increases with latitude. It's larger if you're near the poles. It's smaller if you're near the equator. The reason this is important is because this tells you about the local rotation rate of the Earth at that location. In other words, how much vorticity, that is rotation, is coming from the Earth at the local point that you're standing at, which has a certain latitude and a certain longitude. So phi is typically latitude, lambda is typically longitude, if you think about this point, at least two-dimensionally on a latitude-longitude grid. Okay, remember n is the Brunt-Weissel frequency. That tells us about the frequency if you pushed an air parcel and it oscillated, very similar to a simple harmonic oscillator. It has to do with the restoring force in terms of stratification, in terms of buoyancy. That is, an air parcel that's pushed upward, that's colder than the environment, will sink back down, whereas an air parcel that's warmer than the environment, if it's pushed downward, will rise back up. So that has to do with the restoring force. So anyway, psi here is what we're going to call the stream function. We'll get to that here a lot in this problem. And then what is beta? Well, I'll define that here in a moment, but that's assuming that this Coriolis parameter is not entirely constant, that if you move a small distance north and south in y, so y here is a small distance north and south, that's how quickly f changes with y. And by the way, you could basically just take the derivative of 2 omega sine phi, but you'd have to do it sort of as a derivative and convert the y derivative into a derivative that's kind of in terms of the y derivative in this direction. So you can do it that way, but you have to convert latitude in a clever way. So I'm not going to go through that. But anyway, beta we assume is df dy. So the change of the Coriolis parameter with respect to y. Lowercase q here is what we're calling the quasi-geostrophic potential vorticity. So what is the QGPV? If you look back to the 1940s and 1950s, people like Carl Gustav Rossby and several other people were able to first come up with numerical weather predictions for the first time by taking this quantity as the potential vorticity. And it turns out that a lot of good weather forecasting on large scales, mostly synoptic scales, was done using potential vorticity. Well, quasi-geostrophic potential vorticity says that let's assume that most of the atmosphere is operating in a nearly geostrophic manner. Remember, geostrophic means that the air moves parallel to the isobars, so that is, winds are having the pressure gradient force and the Coriolis force nearly balanced, and what we're saying is that almost all motions are in geostrophic balance, at least horizontally in terms of the winds. Okay? And it turns out that vertical motions are much, much smaller compared to horizontal geostrophic motions. So we're saying nearly geostrophic, quasi-geostrophic. Okay, so there's a lot more to quasi-geostrophic theory. Maybe I'll mention that in a different video. So hopefully in a separate video you'll hear me talk about that. But for now, just you can look up what quasi-geostrophic means. But notice that the quasi-geostrophic potential vorticity, if you follow an air parcel around, so I'll talk about this in a moment. This is what we call a material derivative, sometimes called a substantial derivative, sometimes called a total derivative. But if we tag an air parcel and follow it around to wherever it goes, which is really essentially what you do in a Physics 1 class. But remember, when you're dealing with fluid dynamics, it's hard to find exact air parcels. But if we follow that air parcel around, the idea is that it maintains its quasi-geostrophic potential vorticity, that its change as we materially follow it around is 0. Now, what that also means is if you define the base state quasi-geostrophic potential vorticity and you follow that around, that's also 0. Here's the definition of quasi-geostrophic potential vorticity as given in the problem. And we know that psi is the stream function. Now, as I explain in part 1 of the video, so I refer you to that here, okay, look for the link. I'll make sure I leave the link in the description as well. In part 1 of the video, I explain how that psi, being the stream function, is only going to be for divergence-free flows. Let's assume that there's no net convergence or net divergence in this particular problem. So that's going to be true, thus we can define a stream function. And the horizontal velocity vector, which is made up of the zonal and the meridional velocities. So the zonal is east to west, the meridional is north to south. So what that means is u, which is given by this expression, is in this direction. So any horizontal velocities go in the east-west direction, whereas v, the meridional velocity, goes in this direction. Okay, so that's the direction of v. We're also told that q equals nabla squared psi, but nabla squared, again, is sometimes called del squared. So it's the gradient vector operator squared. We'll talk about that here in a moment. By the way, we do believe, that is, we meaning myself and the other students that were working on this, believe that the professor that came up with this does have a typo. We think that this should actually say zeta. Now, what is zeta? Well, zeta is going to be the vertical component of the vorticity. Now, vorticity is a measure of spin in the atmosphere. Vorticity is going to have units of 1/seconds, but it turns out that the vertical component of the vorticity is going to be the component of rotation. So imagine some rotation here that's in the vertical, and this rotation is perpendicular to the XY plane. It's perpendicular to the Earth's surface. Remember, the atmosphere is not as much three-dimensional as it is 2 dimensions plus 1. The 2 dimensions are the east, west, north, and south. The atmosphere is generally very flat, very thin, and then the vertical things are more stratified. In other words, things really change layer by layer. Okay, so after those definitions, let's go on to the next slide and understand some of these definitions more. This is part 0, just setting up the part 1 of the calculation. So here's the definition of the stream function. We already talked about this. U is part negative partial psi partial y. V is partial psi partial x. Notice all of these equations I have numbered. They're the same numbers I use in part 1 of the video, but it turns out that I just have the numbers on here so that we can always keep referring to the equations as needed. Now here's a proof that the Laplacian of the stream function, which are bowls or mounds of psi, give you the vertical component of the relative vorticity, and why we believe there was a typo on even how the problem was stated. So zeta, which again is the vertical component of the local relative vorticity, is always given by partial v partial x minus partial u partial y. That's just a definition. In fact, if you look at what you might consider to be the curl of any vector field, so if you take del cross a vector field velocity, then it turns out that the z component of this, so if you just look at this in the z direction, it's actually going to be partial v partial x minus partial u partial y, and that would be in the so-called k hat direction, where the k hat direction, this is the unit vector along the z-axis. So this is the definition of zeta. So if we insert these definitions, that is, if we insert v into here, and we insert u into here, notice that the zeta, remember, partial differentiation, you can perform it in any order, and then minus times minus is going to give plus, so you'll get the second partial derivative of psi with respect to x, and the second partial derivative of psi with respect to y, and the sum of those, that's exactly the Laplacian of the psi function. Now, by the way, for the sake of this problem, I'm going to call this
nabla squared or del squared h of psi. Now why h? H means horizontal. So let h here be horizontal, which is just a shorthand for x and y. I've already mentioned this before, that the atmosphere is mostly two-dimensional in the x-y direction. So if this is Laplacian, what is a Laplacian about? Well, for those of you that have studied Laplace's equation before, essentially Laplace's equation says where are the two-dimensional local min or local maxes. Let me briefly try to explain what I'm saying. If you have an upward facing bowl of psi, so this is like a minimum of psi. Notice this minimum of psi is going to produce what? Well, you have to think about this. So if you have the Laplacian of psi, notice the Laplacian of psi, what that's going to be is that's going to be like a second derivative, but two-dimensionally. So if you have a minimum of psi, sort of a bowl, if you will, that's going to be positive concavity. Thinking back to your calculus 1. Well, positive concavity, that's going to produce, based upon this Laplacian, a positive zeta. So if you have a minimum of psi, this is going to produce counterclockwise rotation. Counterclockwise, by the way, is going to be positive in the northern hemisphere, and then for that matter, just in the typical way we define vectors in the x, y, z system that I've defined. Now what about a maximum of psi? Well, we just need to turn this upside down to kind of have a dome, if you will, of psi, and it's just going to be the other way around. We're going to have a maximum of psi, and that means this is going to produce a negative value of zeta. And what is negative going to be? Well, instead of counterclockwise, that's actually going to be clockwise rotation. So clockwise, because again, we have negative concavity. Okay, so I hope that all kind of makes sense. So this Laplacian of psi is going to tell us about where we're going to get local maxes and mins of the vertical component of the relative vorticity. Okay, a couple more equations to define, and then we'll be set up in this part 0 to do part 1 of the problem. Here's the actual definition of that beta plane. Hopefully most of you are aware of what a Taylor series is. What we're saying is that if we approximate f near its particular latitude, we're just saying f is equal to f0 plus the derivative of f with respect to y in the, and then you multiply by y, and then of course in the Taylor series you'd also divide by 1 factorial, but 1 factorial is just 1, and then we would have higher order terms. If we don't go out to the higher order terms, to second order derivative, 2 factorial, and so on, what we're just going to have is that we're just going to truncate at the linear term. Well, if we truncate at the linear term, this is what we call the beta plane approximation, where we define beta as partial f partial y, the derivative of the Coriolis parameter in the y direction only, so in the latitude direction. Now with that in mind, just notice that this is not a perfect approximation, but it's local. We've got a plane which is nearly flat, and it's a tangent plane approximation to the Earth, because we know Earth itself, of course, to be a sphere. Okay, so this is the beta plane approximation, but this enters into our analysis of Rossby waves. Now, by the way, if you've ever had a class that has studied Rossby waves, hopefully your teacher mentioned if you don't have the beta effect, you don't have Rossby waves. That's going to be crucial to this problem. That's also mentioned in part 1. So you have to have changing Coriolis parameter in the north-south direction, so changing with respect to those latitude lines. Otherwise, you're never going to have any effect of the difference in Earth's vorticity affecting the rotation to produce these Rossby waves. And then how about this material or Lagrangian, which is the Parcel tracking derivative? Notice big D by dt is by definition the local change with respect to time. That's the partial derivative of whatever quantity with respect to time. Plus, and these are what we call the advection terms. So these advection terms are generally kind of difficult they make things sort of non-linear because suddenly you have a velocity times a partial derivative of something. Now this particular velocity in this case is going to be the geostrophic velocity in either the x direction or the y direction. So in the x direction it's going to be ug, and the y direction it's going to be vg. Notice x direction of the u and y direction of the v go along with the x and y partial derivatives respectively. Keep in mind we're using ug and vg, that is the geostrophic velocities, because we're in quasi-geostrophic theory. This derivative operator would be more full-blown, more substantial, more difficult to define, or at least have more terms in it that are not as easily calculated if we were outside of quasi-geostrophic theory. Okay, and then let's finally set up the base state plus perturbations of all the quantities we care about in this problem. So we're going to say the quasi-geostrophic potential vorticity is the base state quasi-geostrophic potential vorticity plus its perturbation. Psi is capital Psi plus Psi prime. So remember that's the stream function, and then the horizontal x and y velocities have a background sort of base state velocities. So capital U and capital V, and then U prime V prime. Now, we're told in this particular case that the background is actually a resting base state. So we're going to let capital U equal capital V, and then that's 0 in this case. That's just what we're told. By the way, anytime you have these perturbation quantities, you assume that's a small perturbation from the background base state. Okay, so we typically assume that these perturbations are all small, so that whenever we have a perturbation times another perturbation, we say that's approximately 0, because we don't want any nonlinear terms. Okay, we just only want to linearize this problem to do the fluid dynamics. Nonlinear effects are very hard to keep track of, even with modern methods and computers and differential equations, but we're just going to linearize this problem. Okay, last slide for this video says that in part 1, I'm going to show you that the background psi is only a function of z, not psi itself, but the background psi. So the base state of the stream function only depends upon the vertical coordinate. Furthermore, when we insert that into the background base state of the quasi-geostrophic potential vorticity, notice that the background quasi-geostrophic potential vorticity, the Laplacian of this psi is 0, because remember, this is in the horizontal direction. Then notice that the psi here, which depends upon z, is fine. And then remember, n here, which is the Brunt-Weissel frequency, that also depends upon z, the vertical, so it has to be inside this partial with respect to z derivative. And there's beta y. So remember, y is some distance north or south, let's say from our original latitude, that the Rossby wave has moved. Okay, so this is the setup for the problem. I hope this setup makes sense. You can see the symbols, you can see the equation numbers, and so on. So check out part 1 of the video. I'll leave links to the description of the other videos. And please check out part 2 coming soon, where I go through the rest of this calculation. Thanks very much for watching.
So what we saw in this video is that the setup for this problem, it's important that you really understand the questions, that you really understand what it is that we're trying to do. You understand the methods, the procedures we're going to go through to understand this atmospheric dynamics problem. So this is just part 0, this is just setting up the problem. Remember, the next video, part 1, is been out for a while. You can check that video out. I'll leave a link in the description up here. It's also down in the description of this video. So that video has a couple comments, and it's a lot of you have liked it, so thank you for watching, and let us know in the comments if you want to see more videos on atmospheric dynamics, dynamic meteorology, or things like that. So that is one of my specialties. I love talking about these topics, and I find it very interesting, and I hope it's helpful. So thank you for watching High Peak Education. please smash that like button if you enjoy this content. Please subscribe to the channel in order to grow the channel. Please share it amongst your social networks. We have our own social media links down in the description below, also on this channel. Please support us. We have our website coming soon, and we want to thank you for watching High Peak Education. See you in the next video, part 1, and then part 2 coming soon, where we have the rest of the full solution. Thanks.